Okay, so in this video we're going to have a look at Euler's method again, but this time looking at coupled differential equations. And we're going to look at something called the predator-prey model, which is a really common real-life example of coupled differential equations, where as the number of prey increase or decrease, that will impact the rate of change of the predators as well, who basically eat the prey. So we've got this set up here. These are the differential equations that we're going to work with. And we're going to use Euler's method as an approximation for this. So if I just skip onto the next page, what we'll do is we know that that the units of time is that this is the rate of change happening per month, and we're going to try and estimate the size of each population after 1 year. So we're going to do a step size, like our step size will be 1, so 1 for 1 unit of time, 1 month, and we're going to then do it for 12 months so that we can figure out the size of the population after a year. So we'll go to our GDC and we'll open up a spreadsheet. Let's do the top one here. This is going to be kind of our unit of time. So I'll do time up here, which is kind of going to be months. And I'll do rabbits here and foxes here. Let's start by putting in the initial conditions. So we know that at time 0, we know that we're going to have, how many rabbits do we have? 100 rabbits and 4 foxes. Okay, what we're going to do is we're going to increase the units of time. So I'm going to put in a formula here. I'm going to say equals A1 plus, A1 plus 1. So that's going to just increase my increment of time by 1 every single time. This bit's the bit that's a bit more complicated. Let's just go back to the formula that we've got. So we're trying to work out what the new value of x is going to be. Basically, the new value of x, in this case the rabbits, let's say rabbits are the x values, that's going to be equal to the old value of the rabbits. And then what do we do next? Plus the step size. So we're going to do a step size of 1 every single time. There we go. And we're going to times that by the function that we have, f1, which in this case is the rate of change basically of our rabbits, which is this one here. That's our rate of change of rabbits. So 0.07 times the number of rabbits, 0.07 multiplied by the number of rabbits, that's in B1. And then what have we got next? Minus 0.002 times the rabbits times the foxes. So minus 0.002 multiplied by the rabbits, B1, multiplied by the foxes, C1, enter. Okay, let's do the same over here. So what's that equal to? This is now for the foxes. So it's going to be the initial y value, the previous y value I should say, which is in C1, plus the step size. So the step size we are going for, again, is just 1, multiplied by, let's open some brackets, we are going to type into here the function for the rate of change of the foxes, which is given down here. So minus 0.03 times the number of foxes, so minus 0.03 multiplied by the number of foxes, that's C1, and then what have we got? Plus, let's make sure we get the right number of zeros, 4 zeros in there, so plus 0.1234, and an actual 4, and then we've got that multiplied by the number of rabbits, which is B1, and multiplied by the number of foxes, which is C1. Enter. Okay, so that's our formulae that we've got in there. We now need to drag those down, so we'll copy that down, and we need to do it for 12 months. So I'll try not to go too far. There we go, I think that's going to be that one there. So according to this, we're talking about this as being the number of rabbits, so the population of rabbits has basically increased in that space of time. And what's happened to the number of foxes? The foxes has actually gone down over that period of time. So that's our conditions after 1 year. What's the next question that we've got? The next question says what's going to have happened, what's the maximum value of the rabbit population? Now that's, in a table format, quite a difficult thing to answer. Like what's the maximum value? Over time, I may not have even reached my maximum value just yet. So what I'm actually going to do is I'm going to extend this data quite considerably. I'm going to drag this down, and it's going to keep on going for quite a long way. So let's just keep on going down, maybe for the first 100 cases or something like that. So drag it down to the bottom, just get a bit patient with it. Okay, and I'll release it around about there. So that's down to let's do 101. So that's going to be 100 months that we've done there. Now, I still don't really want to be looking through that whole table of data. What I'd prefer to do is to graph that data. So the way I'm going to do that is I'm going to go Control, Add Page, and I want to create something that's a little bit like a scatter plot, which is in the Data and Statistics page here. Okay, that looks like a horrible mess to begin with. What we're going to do is we're going to have the variable on the x-axis, and we're going to use, for this one, the variable of time. So t, or time, is what I'm going to put on here. And what I'm then able to do is have a look at the fox population and how that's changing. And I'm also able to look at the rabbit population and see how that's changing. And you can see now that I can much more easily figure out where my maximum value is. I can even sort of see the points, but if nothing else, at least I then know where to go back to in the table to try and find which the maximum value was that was reached. So I can see that here, after about 70 months, the maximum rabbit population is going to be 5,802 approximately. And for the foxes, you'll see that the scale has now changed because there's far fewer foxes, as in most systems, there's far fewer predators compared to the prey, and the maximum point, where have we got it? Probably about there. After 84 months, 67 foxes. We can also look at both of them at the same time. Obviously the foxes is on a much, much lower scale compared to the rabbits. But what we can do is we can go onto our menu here. We can look at adding a y variable. So this option down here. So if I add a y variable, I've already got foxes. I'm going to add in the rabbits, and then I'll get both of them being plotted at the same time. It's harder now to see what's going on with the foxes because the scale is, like, the numbers are so much smaller for the foxes compared to the rabbits. Okay, so I've picked out then those key numbers. Let's have a look at one last bit. So this question here then says, what are the equilibrium points for these differential equations? So the key bit of theory here is that an equilibrium point is when the derivatives are equal to 0. So I've quickly calculated those on the next page. I've made dr by dt equal to 0 and solved, and I've made df by dt equal to 0 and solved for that as well. So solving, I've factorized that. That means that r is equal to 0, or if that's equal to 0, that would mean f is 35, or if I factorize the next one, f is equal to 0, or if all of that bit in the bracket is equal to 0, that would mean that r is equal to 750. So those are the equilibrium points. I'll just quickly show you what that looks like if I plot it. So another plot that's sort of interesting sometimes to do, this is probably the one that makes a lot of sense to us, but what we can do is we could instead actually have our foxes here, and rather than having time on this axis, we could change that to being rabbits, which shows quite an interesting kind of graphic here. So we've lost the ability to know what time these things are happening, but we can basically see that as the rabbits increase, the number of foxes is increasing as well. That in turn causes the number of rabbits to decrease, but initially the foxes are going up and up and up until we get to a point where there's insufficient rabbits to kind of feed the fox population, and as a result the fox population will go down. Now what we can do here is we can play around with the starting numbers and see what an impact that has. So for example, if I had more rabbits to begin with, enter, I'll just quickly click on rabbit one more time to just update this. I've actually got a very similar shape for that one. Something very similar taking place with that one there. But we just found some equilibrium points. We found an equilibrium point when r was equal to 0. That kind of makes sense, right? If the rabbits are 0, then I can't increase my population of rabbits because there weren't any in the first place. So basically the foxes' numbers will just go down until the foxes have gone as well because they haven't got any prey to eat. Similarly, if the foxes were 0, I'd expect the same thing to happen. The one that's maybe more interesting is the other values. So when the foxes is 35 Let's put that in. The foxes is 35, enter, and let's put in that the rabbits are 750. If I press enter for that, notice that neither of those values actually ends up changing then at all. But even if I keep that as 35 and maybe change this one a little bit, let's say I put that at 760, notice what happens now. I basically end up, let's just zoom that in a little bit. I'm going to change the rabbits so that it will just zoom that in a bit. You can see that what's actually happening is that these data points are sort of spiraling around the equilibrium point of 750 for the rabbits and 35 for the foxes. So in this particular case, I think they're actually getting ever so slightly closer to it. They're still quite a distance away, but that is the center point around which the data is sort of spiraling or circling. Okay, so that's how we can use Euler's approximations and also how we can kind of interpret some of that information for the contextual questions.